students, welcome in my second video of oscillation. In this video we are going to learn the very important article, that is the linear simple harmonic motion. In shortly we can say that LSHM. This term we understand with the help of one example. Suppose these are the three cases. The one is the spring, the one end of the spring which is fixed to the rigid support, and other end which is attached to the block having mass m. Small m, it is the mass of the block. There are three positions of the spring. The one, the first position, it is the stretched. The second position, it is the relaxed. This is the relaxing position. There is no any force acts on the spring. The force is zero. It is the relaxing position. Then in third case, it is the compressed. This block is compressed toward the left side. These are the three different cases. With the help of this example, we can define the term linear simple harmonic motion. Now in second figure, we assume that this is the figure A, this is the figure B, and this is the figure C. This is the figure C. In A figure, it is in relaxed position. There is no any force act on the block. No any force acts on the block. Okay. Now observe the first figure B. When we move this block toward the right side, and release, such a system which is kept on the frictionless table or horizontal surface. When we move this block toward the right side and release, then it becomes oscillates to and fro about its mean position, and the path is along the straight line. And due to this, it is called as the linear simple harmonic motion. Just we have to discuss this term simple harmonic motion in last video. That is the motion. It is the oscillatory periodic motion in which particle repeatedly moves to and fro about its mean position again and again. Such a motion is called as the simple harmonic motion. When the particle perform the path along the straight line, such a motion is called as the linear simple harmonic motion. And when the path is of a arc of a circle, then the motion is called as the angular simple harmonic motion. In this case, the path is the straight line. Okay. Now, when we move, what happens? Then this spring gets stretched. Due to their elastic property, such a spring which regains its original shape or in original dimension. This spring exert the force on the block, and such a force which is tries to move this block to its mean position. Suppose this is its mean position. This block which moves toward the right side. This is the direction of displacement. X is the displacement from its mean position toward the right side. At that time, the spring exerts the force on the block. And the direction of this force is toward the mean position. And this is the direction of force. This force responsible for the block to trace its mean position or its rest position, and due to this force is called as the restoring force. It is called as the restoring force. That is the F. And this restoring force is directly proportional to the displacement from its mean position of the block. Why it is called as a restoring rest? Because these forces are responsible for the block to trace to its rest position or to its mean position, and due to this it is called as a restoring force, and this restoring force is directly proportional to the displacement from its mean position. When we move the block again toward the right side, what happens? Displacement increases. At that time, the force also goes on increasing. These are the directly proportional. In this case, the force and displacement are in opposite direction, or we can write that this restoring force is equal to K into X, and we can write here minus sign And the significance of this minus sign is that the displacement and force are in opposite direction. This is the direction of the force toward the mean position, and this is the direction of displacement, it is away from the mean position. This is the significance of the negative sign. This K is the constant of proportionality, and it is called as the force constant. This K is called as the force constant. Force constant. And this is a force constant which is depends on the elastic properties of the spring. It is depends on the elastic properties of the spring. And this K, the formula it is given by, from this formula, the K is equal to F upon X. F upon X. And its SI unit is Newton per meter. Unit of the K. Unit of K is Newton per meter. Newton per meter. Okay, this is called as the force constant, and its value depends on the elastic properties of the spring. Okay, these two are the directly proportional. मग याला आपण रेस्टोरिंग फोर्स म्हटले पहा. रेस्टोरिंग का, कारण तो हा ब्लॉक, हा फोर्स काय करतो, त्या ब्लॉकला रेस्ट पोझिशनला आणतो किंवा मेन पोझिशनला आणतो, म्हणून त्याला आपण काय म्हटलंय, रेस्टोरिंग फोर्स. And this restoring force and displacement are directly proportional to each other. Now in third case, that is the position, compressed position, when block M, which is compressed toward the left side, what happened? Then its displacement, suppose this is the minus x, because of left side, according to Cartesian sign convention, we can write here minus sign, there is the plus. राइट साइड ची डिस्टन्स आपण पॉझिटिव्ह कन्सिडर करतो आणि लेफ्ट साइड ची निगेटिव्ह कन्सिडर करतो. दिस इज द माइनस साइन. x it is the displacement from its mean position toward the left side. What happened again? This spring exert the force on the block, and this force tries to pull towards its mean position. तो त्याच्या mean positionला काय करेल, आणण्याचा प्रयत्न करेल त्या ब्लॉकला. मग in both the cases, the common point is that the force is always directed toward the mean position. This is the mean position. ही त्याची काय, mean position. या ठिकाणी फोर्स काय करतोय, स्ट्रिंग त्याला mean positionला आणते आणि इथे सुद्धा mean positionला आणते पहा. The force is always directed towards its mean position. ओके, म्हणजे त्याच्यामधला हा कॉमन पॉइंट आहे पहा. नाउ according to Newton's second law of motion, that is the F is equal to ma. You know that this equation. From this equation, A is equal to F upon m. What is F? F is called here the restoring force. A is the acceleration and m is the mass of this block. Then A is equal to F. This restoring force, it is given by this equation. F is equal to minus K into X. Substitute this. It is the minus K into X and divided by this M. Minus K upon M. This is the constant. The force constant and the mass of the block is constant. Then we can write here this acceleration is directly proportional to the displacement also. Here the force is directly proportional to displacement and acceleration is also directly proportional to displacement. This acceleration and force are directed toward the mean position. And from this relation, we can define the term linear simple harmonic motion. In this equation, this negative sign also indicate that the acceleration and displacement are in opposite direction. In this case, here the acceleration, this is the direction of acceleration and this is the direction of displacement. In this case, this is the direction of displacement and this is the direction of acceleration. These opposite, both are opposite in direction. Okay, म्हणजे एक कॉमन पॉइंट इथं आला की फोर्स आणि acceleration both are directed toward the mean position and both are opposite to the displacement from its mean position. Now here, when we release this block after extension of this string, then this spring get accelerated due to their elastic properties. due to their elastic properties. Its acceleration is increases and displacement goes on decreasing. Displacement goes on decreasing. In this position, when the block attains its original position or mean position, what happens? Its force, displacement and acceleration, these three physical terms are zero at this position. त्याच्यावरचा फोर्सही झिरो असेल, डिस्प्लेसमेंटही झिरो असेल आणि ॲसेलरेशनही झिरो असेल. अँड फायनली इट्स व्हेलॉसिटी ऑल्सो झिरो व्हेन द ब्लॉक प्युअरली अटेन इट्स mean position, then these physical terms are zero. Okay, now from this relation we can define the term linear simple harmonic motion. Now we define the term linear simple harmonic motion, and it is defined as the linear periodic motion of a body in which the force and acceleration, किंवा force किंवा acceleration दोन्ही घ्या, the force and acceleration always directed toward the mean position. This is the direction of force toward the mean position, and in this case this is the direction of force toward the mean position. Also the direction of the acceleration, it is the same as that of the force. Both force or acceleration are always directed toward the mean position, and its magnitude is directly proportional to the displacement from its mean position. Just we have to discuss the force is directly proportional to the displacement. When we increase the displacement from its mean position, the force on the block by the string also goes on increasing. Similarly, in case of this relation, the acceleration is directly proportional to the displacement. हे दोन्ही पण आत्ताच आपण एक्सप्लेन केले आहेत with the help of this figure. This is the definition of linear simple harmonic motion. The linear simple harmonic motion is defined as it is the simple linear periodic motion of a body in which the force or acceleration is always directed toward the mean position, and its magnitude is directly proportional to its displacement from the mean position. This is the definition of linear simple harmonic motion. Okay, the next article is differential equation of simple harmonic motion. Now, just we have to discuss the relation, the force, the restoring force. This restoring force is directly proportional to the displacement from its mean position. Or we can write the next step, the force is equal to minus k into x, minus k into x. Call this as equation number 1. What is F? F, it is the restoring force. Why it is called as a restoring force? Because this force which is responsible for the body to attain its rest position or mean position. K, it is the constant of proportionality, and it is called as the force constant, and its value depends on the elastic properties of the spring, and x is the displacement, and negative sign in this equation it gives that the restoring force and the displacement are in opposite direction. Now from Newton's second law of motion, the F is equal to ma. F is equal to ma. What is m? M, it is the mass of the block. A is the acceleration. Call this as equation number 2. Now A is the acceleration. When we release this block, it is in compressed position or stretch position, what happens? This spring get accelerate. This block get accelerate, and it becomes the acceleration. Acceleration, and its displacement goes on decreasing toward the mean position. This acceleration, define this acceleration. Now this velocity is equal to the rate of change of displacement with respect to time. And acceleration, the acceleration is equal to the rate of change of velocity with respect to time. Or acceleration is equal to d by dt. V is the velocity, and velocity is dx by dt. Or acceleration is equal to d2x by dt square. This is the acceleration. Okay, now these are the two equations of the force. Compare equation 1 and 2, then we get the ma is equal to minus k into x, minus k into x. Substitute acceleration in this equation, then equation becomes m into d2x by dt square, d2x by dt square is equal to minus k into x, minus k into x. Or we can write the m d2x by dt square, this minus sign we take left hand side, it become positive, plus k into x is equal to 0, Next equation, there is equation number 3. Then again modify this equation, d2x by dt square plus k upon m into x is equal to 0. Call this as equation number 4. Now substitute here the k upon m is equal to omega square, where omega square is the angular frequency. This omega square, it is the constant and it is called as the angular frequency. Angular frequency. K upon m is omega square. Then equation 4 becomes d2x by dt square plus omega square into x is equal to 0. Equation number 5. This equation number 3, 4 and 5, these are the various forms of the differential equation of the simple harmonic motion. These are the three various types or various modes of the differential equation. Equation number 3, equation number 4 and equation number 5. This omega is called as the angular frequency, x is the displacement. These are the differential equation of simple harmonic motion. Now we solve one problem, which is a body of mass 0.2 kilogram. One is the body solution, body having mass 0.2 kilogram, performs linear simple harmonic motion. It experiences a restoring force of, the restoring force is given, it is the 0.2 Newton. Restoring force is 0.2 Newton when it displacement from the mean position is 4 centimeter. Displacement from mean position is 4 centimeter. Determine, the first is the force constant. We have to calculate the force constant K. Then period of SHM, that is T. Acceleration of the body when its displacement from mean position is 1 centimeter. 1 centimeter ला mean position पासून 1 centimeter ला त्याचं acceleration किती असेल, या 3 टर्म विचारलाय. We find one by one. The first one is the force constant K आपल्याला फाइंड आउट करायचं आहे. What is the formula? According to restoring force is equal to minus k into x. हे इक्वेशन आपण पाहिले. Magnitude of this equation is F is equal to k into x. K is the force constant. Then from this relation, the force constant is given by k is equal to F upon x. Substitute this value. What is F? F, it is the 0.2 and x it is the 4 centimeter. Now convert it is in meter. The 4 into 10 raised to minus 2 meter. आपण ते मीटर मध्ये करून घेऊ. Divided by 4 into 10 raised to minus 2 meter. Then force constant, its value is given by, it is the 5. The calculation of this figure is the 5 and the unit is Newton per meter. This is our first answer. Force constant. This is the force constant. Now second. What is second? Second is the period. Period T is equal to, what is formula? It is a 2 pi upon omega. General formula period. 2 pi upon omega. That T is equal to 2 pi. What is omega? Omega, just we have to discuss the K upon M is equal to omega square. Then omega is equal to square root of K upon M. This is 1 upon omega. That is M upon K. It is the square root of M upon K. This is the formula. Then period. Substitute this value. 2 pi is the constant, 3.142. Mass is the given, 0.2 kilogram, and K is the force constant. Just we have to calculate it here. Substitute this all value. Then its value period is given by substitute this value. Then period is given by 0.4 pi, and the unit of period is second. This is the second answer. This is the period. The value टाका आणि त्याचं calculation करा तुम्ही. Now the third is the acceleration. We have to find the acceleration when its displacement from mean position is 1 centimeter. 1 centimeter ला इथे displacement 4 ला दिलंय. आता 1 centimeter ला आपल्याला ते find out करायचंय. Then our third point is the acceleration. When acceleration is equal to, आपण पाहिलं equation, it is equal to minus K upon M into x. This is the minus sign indicate that acceleration and displacement are in opposite direction. हे आपण मागच्या आर्टिकल मध्ये डिफाइन केले पहा. K is the force constant and M is the mass. आपल्याला डिस्प्लेसमेंट 1 सेंटीमीटर ला सांगितलं पहा. X is equal to 1 centimeter. Then it is equal to 1 into 10 raised to minus 2 meter. Substitute this value. A is equal to minus K. What is K? K is the 5. M is the given 0.2 and into x. X is the 1 into 10 raised to minus 2. म्हणजे तो एवढा येईल. Calculate this. We get the A is equal to 0.25. The unit of acceleration is meter per second square. Or we can write here negative sign, minus sign. जे फॉर्म्युल्यामध्येच आहे त्याचं सिग्निफिकन्स काय की डिस्प्लेसमेंट आणि ॲक्सेलरेशन हे काय असणार आहे अपोजिट डायरेक्शन असणार आहे त्यांची. दिस आर द थर्ड आन्सर. दिस वन इज द थर्ड आन्सर. ॲक्सेलरेशन इज इक्वल टू minus 0.25 meter per second square. Okay, thank you.